little bit more notation for x and y in n. They are similar if their lambdas are equal, so if they have the same minimum support point. One is infinitely greater than the other if it has a lower minimum support point, and they are similar equal if they are similar and they agree at the minimum support point. So they're they differ by a relatively infinitely small amount to their highest order, or lowest, I guess. Okay, so we have a definition of order in n, what's greater or less than. So we have two that are unequal. We say that x is greater than y. If x minus y evaluated at their minimum support point is greater than 0, and we can reverse this order. So if x is less than y is greater than x. And this order induces an absolute value in kind of the natural way that everyone would expect. And we can define this absolute value will define an order topology in also the natural way in a little bit. But an important element of these non-Archimedean fields is this element d, which is the unit of infinitesimal. So d evaluated at r is 1, if r is 1, and 0 for any other r. So it's a function with one support point, and it's obvious to see that dr is infinitely smaller than 1 for all r greater than 0, and dr is infinitely greater than 1 for infinitely less than 1 for all r less than 0. And of course d0 is 1. So if you imagine these functions, right, in a 2D graph, all the real numbers would be just the real line going up at 0. D would be a single point at x is equal to 1, right? And if you multiplied d by d, it would move further out to the positive side. And that's moving further and further into the infinitesimals, if you can imagine that. Whereas if you took the inverse of it, it would flip over to -1. That would be the only support point. And going towards the negative numbers along the x-axis of these functions is going higher and higher into the infinities as opposed to infinitesimals. So we can reimagine any of these functions as a sum over the support points of x evaluated at the support points times d to the order of the support point. So it would be a sum of these dots along our real axis at varying heights that give the coefficient and then the order, if that makes any sense. Okay, so why are we thinking about these fields? And, how are they different, right? We know that there's an order topology. We have some I guess, weird way of expressing elements, but what do we do with them? And we can do, the topology is completely disconnected, so some weird stuff can happen. So if we imagine a function that's f of x is equal to 1 for x infinitely smaller than 1, and 0 for all else, and we'll just define this on 0, 1, because why not? Okay, so for all x and n, we have that the minimum support point of x plus dx, the absolute value of x, is equal to lambda x. If we take the lambda of a function plus an infinitely small number, or a relatively infinitely small number, it's going to be the same thing. It's not, you're only changing the minimum support point. So if you change a support point over here, it doesn't matter. It's not changing the minimum support point. So that means that we can say that this statement here, this f of x minus f of x plus dx is equal to 0. So for all x naught in n, for every epsilon greater than 0, there exists delta equal to d times the absolute value of x naught greater than 0, such that for all x in our delta ball around x naught, f of x minus f of x naught is less than epsilon. Okay, so it's a continuous function. However, we can see obviously that there's no intermediate values between 0 and 1. So it's completely disconnected field, and that gives us that continuous functions don't have intermediate values. So if you want to do any kind of integration, you need to find a class of simple functions that can have intermediate values. And since this is defined everywhere, the derivative is 0 everywhere. Right? But obviously, f is not constant. Okay, so these are just a few points that I feel like I should mention, but they're theorems that we couldn't go to proving. So these are just the convergence criterion in N for power series. So yeah, the limit as n goes to infinity, an is equal to 0, if and only if the sum converges, which is very nice because it makes convergence tests very easy. And then for power series, this expression here, which is not really super important. I just feel that I needed to say it because otherwise, we know that power series converge in this field, essentially. And we have a criterion for it, but it is hard to prove, and I don't have enough time. And it's not super relevant, but it should be here. Okay, so how are we going to find intermediate values? What we want to do is use a modified non-Archimedean version of the Banach fixed point theorem. So if we let Qm in R be given, we define M as a subset of our non-Archimedean field extensions of real numbers that have greater lambdas than our Qm, right? So these are small or around Qm. And we let a function from M to M be defined such that it's pretty much that it's a contraction, and it's a contraction where the contracting factor is infinitesimal. Right. If we have this, much like in the real case where if we had the contracting factor was simply less than 1, then we get a unique x such that f of x is equal to x. Okay, so we have to be very quick. Sorry about that. So we give ourselves a convergent power series on a closed interval, and we define a new power series sort of just to make it from A to B to 0, 1, where sort of without loss of generality, we have that f0 is minus f1, so take f0 to be negative, f1 to be positive. And we'll look for a single intermediate value because we can just, like adding a constant won't change the existence of intermediate values. We can just use the same proof for g is equal to f minus s. Because all of these, there exists an n such that an is strictly less than d to the minus r for every r and r. So that means that we have some finite number of terms that are contributing an amount more than a particular infinitesimal. So we can define a coefficient that will give us a 0 index on the function, which pretty much means that we can get a real power series, fr, which is just the sort of the function evaluated at the 0 score points. Okay, so because it's a real power series on a closed finite interval, it will have finitely many roots. And so we find an interval CD where f prime r is not equal to 0, and we guarantee an x in CD such that f prime r x at 0 is equal to 0 because there's an infinite amount of possible offsets, so we can move this function up and down to get such an x. All right, and then there's a few cases where that's more difficult, and we have to be careful and clever about our offsets in ways that are not super relevant. Okay, so if we essentially we use the real intermediate value theorem to get a real value where fr at x is equal to some an intermediate value that we're looking for. So in this case, 0, right? If we have that f at big X is equal to s, then we're done. So we'll assume that we don't have that, that we're infinitesimally close. And just doing a simple power series expansion, except for we just call the final terms r, because we don't really care about all of the higher order terms after order 1. We've taken f prime at x to be at most finite. So well, in fact, exactly finite. So we just divide by it, we're allowed to do that. Eventually, we get this h, which after some doing, we can show is in agreement with this, in fact, where we have c is d lambda s. And then obviously, because this f prime at c and d is non-zero, this x plus little x isn't 0, 1.
Thank you.
Yeah.
Okay. Any questions for Will?
Yes.
So obviously, since we have this theorem that like the real numbers is a complete ordered field, is like any other complete ordered field that's Archimedean is isomorphic to the reals. Is a same kind of thing happening here where we can potentially make this isomorphic to some other complete ordered field that is non-Archimedean and do work there, or is it strictly set up for just this field?
Yes, in fact, we're working in a generalized non-Archimedean field extension of the reals. So there you could have more rules than the support points for functions in the field are well ordered. So for instance, in the Levi-Civita field, they are left finite, for instance. And so essentially they're all isomorphic to this class of fields. Yes?
Last question?
Hi. I'm not really familiar with this non-Archimedean analysis, but is it possible that there could be any applications to topological biology, particularly some inconsistencies in the Endler theorems and this avian contradiction, right, like this? I know this is kind of out of...
Yeah, you know, I mean, the topological biology tends to have a lot of sort of real-based stuff, just because it's sort of like finite measurements and stuff.
Yeah.
Anal was doing some interesting work in Germany, but I mean, it's a little over my head. I guess what I'm trying to say.
Okay, thank you.
But what would you see as being perhaps the most direct physical relevance of your work?
It's difficult to say exactly where this is going to come up in physics. Some people have been speculating that maybe Planck length and Planck time don't scale in the way that we think that they should. But I mean, we have real values for it, so saying that it's non-Archimedean is obviously it's too bold. But a system where infinitesimals are a thing that you can deal with is, in the very least, valuable for kind of perturbing systems a little bit, and you can get solutions pretty quickly. In particular, the Levi-Civita field is sort of well behaved enough that computers can deal with it. So you can get very fast solutions to derivatives and stuff. Again, I wouldn't try and be bold and say that I have a good physical application for it just yet. And mostly this is in aid of, again, developing a class of simple functions such that we can do integration on this sort of space. And then once we can do that, obviously physical things become a little bit more feasible.
Thank you, Will.